Hello everyone, I'm Dr. Matlab. We resume our course. We've completed the first two steps, where with the first step we got this factored form, and with the second step we determined how many digits to keep after the decimal point for each zero and each pole. Now for the third step, we suppose that we already got this factored form, and we suppose that we determined how many digits after decimal point we keep for each zero and each pole. Now the third step says the poles and the zeros are arranged according to the values of their moduli. What does it mean that? Let's take this example where we have again and an integrator and n of z over d of z. Okay, now what are we going to do? If I take this numerator, in fact I will place the polynomials respecting the descending order of the moduli of the corresponding zeros. The same for the denominator. I will place the polynomials respecting the descending order of the moduli of the corresponding poles. We already know that this arrangement is just for n of z over d of z, just for this part. Okay, now we continue with this example to understand better. For the numerator, we suppose that the modulus of z2 is higher than the modulus of z1. And for the denominator, we have here a polynomial of degree 2, so we have here two complex conjugate poles. For the denominator, we suppose the modulus of b1 is higher than the modulus of b2. Okay, we can observe that this inequality corresponds to this inequality. The modulus of b1 is higher than the square root of b0 because b0 is equal to the square of the modulus of b2. So the modulus of b2 is equal to the square root of b0. Okay, so this inequality corresponds to this inequality. Okay, now how to arrange the polynomials for the numerator and the polynomials for the denominator. In fact, as the modulus of z2 is higher than the modulus of z1, I will put this polynomial first, then I will put this polynomial. Why? Because the modulus of z2 is higher than the modulus of z1. Now for the denominator, I will put this polynomial first. Why? Because the modulus of p1 is higher than the modulus of p2, where p2 is a complex conjugate pole for this polynomial of degree 2. Okay, now we arranged the polynomials for the numerator and the polynomials for the denominator. Okay, now for the fourth step, we will write this part n of z over d of z as a product of smaller transfer functions. As you see here, we have here this small transfer function, we have here another small transfer function until nb transfer function. Okay, so what did we do? In fact, we broke down this part into smaller transfer functions. Okay, each transfer function, each block can be first order transfer function or second order transfer function. That depends on the degree of the denominator of each block. If I take this block, if I take this small transfer function, if the degree of this polynomial is 2, so we have here a second order transfer function. Okay, now we go back to our example. I will break down this part into smaller transfer functions. So I take this polynomial over this polynomial and I obtain this block, this small transfer function. Then I have this polynomial over this polynomial, so I can obtain here another small transfer function. So for our controller, we have here three blocks. We have already our integrator, and we have this transfer function, and we have this transfer function. Each block is first or second order transfer function. Okay, now for the fifth step, and with the first point in this step, I will write our controller as a function of z power -1. Okay, for our example, for the integrator, we multiply the numerator and the denominator by z power negative 1. And for this block, I multiply the numerator and the denominator by z power negative 1. And for this block, I can observe that we have here a polynomial of degree 2. So I will multiply the numerator and the denominator by z power negative 2. Okay, now for the same example, I will suppose for the denominator, the modulus of P1 is less than the modulus of P2. So I will put first this polynomial of degree 2. Why? Because the modulus of P2 is higher than the modulus of P1. Now we will break down this part into smaller transfer functions. So I take this polynomial over this polynomial and I obtain this block, and for the other block I have this polynomial over this polynomial. Okay, then we write our controller as a function of z power negative 1 as we did before. Okay, now we will take several numerical examples to understand better. Let's take this example. Now we will arrange the polynomials for the numerator and the polynomials for the denominator. We can observe that for the numerator, the modulus of this 0 is higher than the modulus of this 0. So I put this polynomial first. Okay, now for the denominator, I can observe that the modulus of this pole is higher than the modulus of this pole. So I will put this polynomial first. Now we will break down this part into smaller transform functions. So I take this polynomial over this polynomial and I obtain this block, and I take this polynomial over this polynomial and I obtain this block. Okay, now we will write our controller as a function of z power negative 1. Let's take another numerical example. We have here just a polynomial of degree 1, and for the denominator we have two polynomials of degree 1. For the numerator, there is nothing to arrange because we have just one polynomial. Now for the denominator, we have two polynomials. We can observe the modulus of this pole is higher than the modulus of this pole. So we will put this polynomial first. Okay, now we will break down this part into smaller transfer functions. So I take this polynomial over this polynomial and I obtain this block. And for the other block, I have 1 over this polynomial. Now we will write our controller as a function of z power negative 1, as you see here. Now let's take another numerical example where we have here just a polynomial for the numerator, and for the denominator we have a polynomial of degree 1 and a polynomial of degree 2. As you see here, for the numerator there is nothing to arrange. Now for the denominator, we have here a polynomial of degree 1 and polynomial of degree 2. For the polynomial of degree 2, what interests me is the complex conjugate pole. As you saw before, the modulus of the complex conjugate pole is equal to the square root of this value. So the square root of this value is equal to 0.5. As 0.5 is higher than 0.3, so I will put this polynomial of degree 2 first. Okay, now we will break down this part into smaller transfer functions. I take this polynomial over this polynomial and I obtain this block. Then I have this block which is 1 over this polynomial. Okay, now we will write our controller as a function of z power negative 1. You can observe that here for this block, we have here a polynomial of degree 2. That's why we multiplied the numerator and the denominator by z power negative 2. Okay, now let's take another numerical example. We have here for the numerator a polynomial of degree 2, and for the denominator we have polynomials of degree 1. For the numerator there is nothing to arrange because we have just one polynomial. For the denominator we can arrange these polynomials as we did before. We will put this polynomial first because the modulus of this pole is higher than the modulus of this pole and this pole. Then we put this polynomial because the modulus of this pole is higher than the modulus of this pole. Now how to break down this part into small transfer functions? If I take this polynomial of degree 2 over this polynomial of degree 1, I obtain a non-proper transfer function. Why? Because we will obtain a transfer function where the degree of the denominator is less than the degree of the numerator. So for each block we have to obtain a proper transfer function. proper transfer function, that means the degree of the denominator is equal or higher than the degree of the numerator. Okay, so I can't take this polynomial over this polynomial. So how to do? In fact, I can multiply this polynomial with this polynomial, so I can obtain a polynomial of degree 2. Okay, so I can take this polynomial of degree 2 over this polynomial of degree 2. So I can obtain here a proper transfer function. That means the degree of the denominator is equal or higher than the degree of the numerator. Okay, then I can obtain this block. Now we can write our controller as a function of z power negative 1. Okay, now we did the first point in this step, the step 5. We will continue with this step. We will explain how to write our recurrence equations from this form. Okay, and we will explain how to apply these recurrence equations in a microcontroller. We will take a numerical example and we will explain how to apply the recurrence equations in a microcontroller. Wait me for the following videos. Don't forget to subscribe to my channel. Thank you for your watching. Goodbye.